But of course, you can think of this as like a ranking of sports teams, okay? If the best team is the one that most gets to get rid of electrons. So this is like your rankings. So the top teams are the best, the bottom teams are the worst, and then you have some teams in the middle. These are the ones that have a 500 record, right? They win some, lose about the same. No real preference. It really just depends. If they're going to win or lose, it really just depends on who they compete with, right? So you could take, for instance, glass and hair, which are both prefer to be electron donators. You can also put them head to head. It's like the #1 team playing the #2 team. What will happen? Well, glass and hair, glass will become positive and hair will become negative. Even if the #2 team could beat everybody else, it's going to lose to the #1 team. So you can't say that hair rubbed against everything is going to become positive. If it's rubbed against most things, it will be positive. But it can also become negative if it's rubbed against something that is even better than, and even higher in the series than that. So you have to really be careful to, when electrons, acceptors, and donators, this is not a you're one or the other. It depends on who you're playing, okay? So any substance higher on the list rubbed against any one that's lower on the list, the one that's higher is going to be plus, the one that's lower is going to be minus, okay? In fact, if you did this competition, you'd have very little transfer, very little charge transfer. And that's because, of course, they're both donators. They're both thinking, hey, you take those electrons. No, you take them. No, you take them. And somebody eventually is going to be like, oh, fine. Okay, I'll take a few. But there's not going to be as much charge transfer as if you combine two things that are drastically on opposite ends of the spectrum. Okay? So I think you probably do a lab at some point on this. Did you do it already? Okay, so yeah, so when you get to this, they're not going to give you glass and hair to rub together because the amount of charge that would be transferred would be so little you won't notice it. They're going to pick, hopefully, substances that are pretty far across, so then you'll actually notice the charge being transferred. And once you've transferred it, they, of course, are going to stick together. Okay? So static cling. You do this all the time if you forget to put the dryer sheet in the dryer, right? So you're putting in all these different clothes of different makes with different ingredients, different locations of the triboelectric series. They rub against each other, they transfer charge, and then you're trying to peel them apart, right? Question?
Why does that get worse in winter?
Because it's dry. So it turns out that water is a place that water conducts electricity pretty well, so it lets the excess charge dissipate. So anytime you have moisture in the air, static electricity doesn't build up nearly as easily. So the classic example is that that lab happens in like the first couple weeks of the spring semester, and it's raining cats and dogs, and then the lab doesn't work at all. Okay, so that's a little bit about the triboelectric series. I guess I should say a few words about why is it that you have to rub them together. Well, here's my analogy. So let's say you went to your college graduation, right? You guys all got your bachelor's at this point, right? So you went and you had your gown on, you had your mortarboard, okay? Everyone has a hat, okay? And they give some speeches. It's very hot out, or it's rainy, it's some horrible weather, and someone that you've never heard of is giving a speech, and then you walk away, and you probably have one hat still. But you may note that some places they do this, this old tradition where they throw the hats up in the air, right? At the end of the ceremony. Did anyone do this? I think they outlawed it at my school because they were afraid someone was going to get hurt with a falling hat. So let's imagine that everyone throws up their hat, okay? So you throw up your hat, and then maybe pick up a hat, and it might not be your hat, but you have a hat, okay? And then you go home. Well, when those hats are being thrown up, there are some people that are going to be like, throwing your hat up, okay, screw this, I'm leaving. Okay, so they just leave their hat behind. There are other people who love hats, and this is their opportunity to get more hats than they came with. Okay, so it's important that there be some energy injected into the system. Okay, and that's exactly what's happening when you're rubbing these two things together. You're basically taking some electrons, putting some energy, promoting them into a higher state, and then when they fall back down, they're going to fall back down not where they came from, but more unevenly depending on who wants it more and who wants it less. And that's where the charge transfer comes in. So there needs to be a little bit of energy injected into the system, right? Hats being thrown up. Okay. Okay, so you'll get a chance to try that out, hopefully. And the next order of business we have is to start to take materials and characterize them in a different way, split them up basically into two categories: conductors and insulators. Conductors and insulators. So, first of all, for full disclosure, we are going to be making an artificial distinction and for the moment pretending that materials are either conductors or they're insulators, when in reality, as with most things in nature, it's not so clear cut. In fact, by the time we get around to homework 3, I think, we're going to loosen these boxes to a distinction. Loosen the distinction to a continuum. So I'll explain that in just a second. Let me tell you what a conductor and an insulator is. A conductor is some piece of material where, obviously, if it's a solid piece of material, that means that there is atomic bonds happening. So you have molecules, some kind of crystalline structure. It's not like a gas. There's positively charged nuclei, which consent to be near each other instead of flying apart because, of course, they've come to some agreement with each other's electrons, right? That's what holds matter together, yes? This chemistry, yes? Okay. So, in addition to the minus charges that are basically around each atom, each nucleus, like that, they're also floaters. So there are electrons which don't particularly belong to any nucleus. These tend to be the higher energy electrons. You have the lower energy electrons are in the valence band, but then there are these high energy electrons that are floaters, okay? So I'll kind of intersperse some floaters. They're in what's called the conduction band. So there's the valence band, which are bound electrons, and then there are higher energy electrons, which are called conduction electrons. So there is a large number of electrons that are not bound to any particular nuclei. Now, I'm not saying, again, all of them, but there are still, it's a vast quantity of electrons that are available to float wherever in the bulk of the material they may be called on to go or desired to go. We'll, of course, give them some reason to do that later. But for right now, just understand that they are somewhat free. That is to contrast with an insulator, where all of the electrons, I guess I'll just draw the same thing without the floaters. Oh, this is going to take a while here. Let me just So I kind of draw like this. It's like a little pen, right? So we'll say that those particular electrons can't really leave that region. They're basically rooted to that local region around that particular nucleus. Okay? So here we have that the electron are bound to particular nuclei. Now, as to why this is a complicated answer as to why certain substances have these floaters and other ones don't. And what we're largely going to do is say, if that is true, let's follow through the consequences of what that would mean. Okay? I guess the analogy I would give, this is like the communist system. Okay? Electrons are shared. And here's the capitalist system. Okay? So ownership, electrons are owned. Someone got really offended by this. I'm not endorsing any particular system. I'm just using an analogy. Okay? And it's not even really like this. Okay? It's not really that you're one or the other. There is a continuum of behavior of how free versus not free these electrons are to roam. We're going to rate that later with a property called resistivity. Electrical resistivity is a rating for just how not free or free these electrons are. Some of the most important applications are in the nether regions between these, something called semiconductors. So a semiconductor is something where the electron's not free to flow around unless you give it a little bit of a coax, and then it is free to flow. So you can control the flow of electricity very readily. And all of you have undoubtedly have a semiconductor device on you right now. They're used for what? Transistors, yeah. So the two most famous, the most famous semiconducting material is silicon, right? Silicon Valley. Okay, so this is what they use for computer chips. So logic gates and things like that for computing. I'm sure you have some amount of semiconducting material in your smartphone on your person right now. So we'll get to this later. But for right now, it's very informative to compare and contrast the behavior of conductors and insulators in the types of situations that we might apply. So let's go ahead and get started on that. So let's maybe involve a conductor and or insulator in a charging by contact. So hey, let's just rub two things together. Let's rub a conductor and an insulator together. Now, being a conductor or an insulator doesn't necessarily mean you're a donator or an acceptor, but I'm just going to pick, let's say that electrons get transferred, I don't know, let's say they get transferred to the conductor. Let's just suppose that that's the direction, so I have something to draw. So here's the thing. There's no charge mobility in an insulator. So where did you get those electrons in the insulator? You got them right here. So that part where you rubbed the other thing to it, that's where you got them. Now, those electrons are going onto a conductor where they can feel free to roam, and minus charges do not like to hang out near each other. So they're not just going to stay all on the edge here. They're just going to redistribute. They redistribute to the surface because that's how they can maximally repel. If they're mobile, then that's where they want to be. So we have our first factoid about conductors versus insulators. In an insulator, the net charge is wherever you put it. You rubbed on the left side here, that's where the net charge is because it doesn't have an ability to redistribute. Over here on a conductor, where does the excess charge live? It always redistributes to the surface. It redistributes around the surface. So I'm going to start a master chart and then finish it next time of various phenomena, singular phenomenon, I'm going to list it. I'm going to ask, how does it work for a conductor? And how does it work for an insulator? And the first thing that I just talked about will be my first entry. What happens when you add excess charge? What happens if this type of material is charged up? It's not neutral. Well, the excess charge on a conductor lives on the surface. It redistributes around the surface. And the insulator, wherever you put it. That's the difference between having charge mobility versus not. Okay, so that's my first row. Let's see if we can get another row in today. The next thing I'm going to do is I'm going to take a conductor, which is neutral. This is a neutral conductor. And I'm going to put it into an external electric field. Who knows what the cause is, but there's an external electric field applied. Let's just, for the purposes of simplicity, make it the simplest possible. It's a uniform electric field. Maybe it's caused by an infinite plane or two infinite planes, parallel plate capacitor. It doesn't matter. Let's say there's an external field. So what happens? You might think, well, nothing, it's neutral, but something does happen. Remember that a conductor does have a large store of mobile charges within it, and those mobile electrons say, hey, there's an external electric field. Let me go upstream to that. So they go over here. They stop there because they can't just jump off the material. But they're mobile inside there, so they go upstream. They swim upstream. If you try really hard, you can pull them off, by the way. We'll talk about that later. But for right now, that's the end of their journey, right, is to move to the left side. Well, that means that there's an equal number of positive charge on the other side, those protons that got left behind, because this thing is still neutral overall. It's still neutral, but now the charge is not all mixed up on the atomic level, plus, minus, all willy-nilly, all interspersed. We have a definitely more negative charge on the left side and more positive charge overall on the right-hand side. We've been able to achieve a macroscopic separation of charge. We call this charge polarization. Charge polarization. Separation into extremes. Just like political polarization. Okay? Trump and Sanders, right? Way different. So, what becomes of this charge polarization? Well, we can actually do a lot with it because it's a way for us to separate out charge macroscopically instead of having to sift it out on a tiny, tiny level. I should point out that when these negative charges move to the left, they clunk up against the inside of the surface, and they continue to push to the left. They just would have to take the whole object with it if they wanted to move to the left some more. And these positive charges are going to get pulled to the right. But what do you think happens to those two forces? They cancel, that's right. So the net force on this thing is still zero. So we've achieved charge polarization, but the conductor, neutral conductor, won't go anywhere. Okay? So adding to my phenomenon here, charge polarization, can you have it? Yes, you can on a conductor, for sure. Just like we just talked about. You may say, well, insulator doesn't have charge mobility. I guess that's not going to work. But it turns out that there's another trick up the sleeve of an insulator. And the answer for an insulator, generally speaking, is going to be, it does the same thing, but not as well. But before I get to the insulator, which I'm not going to have time for today, I do want to point out that we could, instead of having this external field be uniform, let's have it be non-uniform. Let's have it be like this. It's going to weaken as it goes to the right. And then let's put that same neutral conductor in there. So same thing, minus, minus, minus. Charge polarization, plus, plus, plus. So the charge again separates out. But now the forces are on the two halves of the charge polarization are going to be unequal. These negative charges are in a stronger field and feel a stronger force, and then the positive charges on the right are in a weaker field. So what's going to be the direction of the net force? To the left. So the net force here will not be 0. The object will actually, despite being neutral, be pulled into the region of stronger field. So the net force was 0 here only because it was a uniform field, whereas here the net force is not 0 because it's a non-uniform field. Now let me remind you, already we learned earlier today that a uniform field is the exception. That's very rare, and a very contrived charge distribution needs to be present to make such a thing. Most electric fields are like the one on the right, the non-uniform. What would be an example of something that can make this? How about some charge, right? The electric field gets weaker as you go away from it. So what do we notice? We notice that the neutral conductor is attracted to the charged object. So that's a correlation that's a third option that you may not know. Opposites attract, like repel, but neutral objects are attracted to everything. A neutral object can be pulled into a charged one. Okay? So we have a charged and uncharged object are attracted. The only thing that has to happen is for the charged objects to have a non-uniform field, which is pretty much true all the time, and the uncharged object to have a finite size, which again, objects have finite size, which means that the charge polarization can happen. And then one half of the charge polarization is in a different field strength than the other, and the net force will always be into the region of stronger field, which then means towards the charged object. You've probably seen this. Okay, when you take those clothes out of the dryer, right? You pull them apart, right? You have two charged things. Take one of them, throw it away. Okay, so you have one charged object. It sticks to everything. Sticks to you. Sticks to the wall. Sticks to the dryer. That other thing is all uncharged. But once you're charged, you attract to uncharged things. Okay, so charge polarization, yes. And adding to that, that means attraction of charged and uncharged in a non-uniform field. So charge polarization, it need not lead to attraction if it's in a uniform field, but most likely, if it's a non-uniform field, there will be attraction. So following right behind the heels of charge polarizing will be an attraction. Okay, so let's leave it there for today. I think I'm out of time if we'll ever get a block in here. Yeah, so we're out of time. So we'll pick up how does the insulator participate in this, and we have 2 more rows to add into this. And after we do that, which we'll finish next lecture, we'll finally get to the energy method.